15 minutes. And I want to thanks a lot, first of all, and thanks for those who were helping me to put things together, sending some notes, and so it was very useful. I want to ask you help also. I try to be as accurate as possible, but doesn't mean I'm going to be. If something is not fully accurate, or some ideas are missing, or something is incorrect, I would highly appreciate it if you could come during the coffee break. I can amend it, and maybe I can provide a final version to the organizers before lunch that probably is useful for them. So apologize in advance, because if something is not accurate or completely aligned with what you say or what you wanted to say, it's all my fault. But let's try to make it properly by lunch, okay?
Thank you. I mean, we just very much appreciate pulling this together.
So, yesterday we have a full day. We were basically touching 2 points. Next slide. Can I pass it? Yeah. We're touching 2 points, technology and investment, and we have an opening by Carlos Alejandre, which I think put fusion in the context of why we need this new source of energy. So I will go through. You will see some of the ideas are repeated in the blocks, but repetitions and how it's good because you fix the idea in your mind. So we started this introductory talk, keynote, saying, or giving the information that we have a rising energy demand. We need to diversify the energy mix. We need to have a systemic approach in Europe. We need to work on energy in grids and in transmission. All these elements, we need to be able to fit fusion in all these elements. And probably this is part of our job, to try to raise our voice in that groups, provide information to put fusion into this context. We have seen a number of breakthroughs and progress in the last years in inertial, in magnetic confinement. But nevertheless, the technologies involved remain highly complex, and we have a number of gaps that we will see in the next slides. We saw also the need of strengthening the EU supply chain and how this way has been paved strongly by ITER already, so this is a really good and a strong point in Europe. And the last idea that I wanted to highlight is that fusion has to be cost competitive to penetrate into the market. And this is something that maybe for the first scientific plan, for the pilot plan, is not the driven factor, but we need to keep it in mind because that is an ultimate goal, to be able to provide an energy that is cost competitive. So with that context, we go into the main session of technology in the morning. So we have the keynote by Gianfranco, where he reminds us the technical challenge, and it was also that it was a topic was discussed also in the working groups. So one more, the technical challenge that remain to be solved is the tritium breeding and the fuel cycle, mainly related to the blanket, the power source management related to the divertor, remote maintenance related to blanket, mostly materials under neutron exposition, also blanket affected, heat extraction and conversion, blankets and advanced magnets. Although in the advanced magnet, a lot of work is being done. And overall, on top of all that, we need integration. We need to be able to put all these subsystems together and test it and see that it works properly. All the subsystems are in very low technological readiness level, below 4, because they have not been relevant, they have not been tested in relevant conditions, and safety implication needs to be taken into account when we design all these subsystems. And so, during yesterday, we have a number of discussions of the needs of IPMIF donors, of volumetric neutron source, how to take advantage of the existing information. So it's something that it was the whole day, I think, on the table. So once more, these are important testing facilities to be able to advance technological readiness level. Later on, we were having a little bit of information about plasma performance and how these high-temperature superconductor are making tokamaks to be smaller and cheaper and faster. That was given by Pablo. That was very kind to pass me some sentence. So core transport simulation and performance predictions has been recently achieved as a level of 100% fidelity, thanks to improved understanding of plasma dynamic, hardware and computing, and machine learning. And I would like to highlight that thing because this is one of the key elements coming from enabling technologies. We have now these new tools that are making fusion, I wouldn't say easier, but more affordable for human beings to be able to develop it on Earth. Reactor design studies now need to take a full advantage of these improved simulation capabilities to mitigate risks, reduce uncertainties in the prediction, and find optimized plasma solutions that can lead to a faster advancement and more efficient plasma experiments. This is the key. We can go now faster. We can be more efficient. We can be more precise. But don't forget that at the end of the day, you need to test experimentally. No one is going to replace this experimental test, but we can do it more efficiently, more accurate, and need less experimental tests than before, thanks to these new tools. And this is a huge difference. After that, we have the presentation of a Spanish project, the Spanish project, I will say, by Manolo, the SMART project. The SMART project is an spherical tokamak, high temperature magnets with negative triangularity. This is very unique. We have the problem of extreme power source. This is a limit, and this is overcome by this configuration in negativity triangularity that makes that thing that seems to be impossible, possible. SMART is built in Sevilla. It's a proof of concept. It's the first step for a more compact fusion power plant. It was built in 2 years and is online since 2024. The next step it will be ES-SMART, which is expected to have a Q higher than 25. It's a compact machine, and between SMART and ES-SMART, the plan is to make an intermediate machine that could be used easily as a volumetric neutron source, and that will have high temperature superconducting. So we later on saw another project by Susana that presents a SIMR. This is an inertial fusion approach, which is good to have this understanding. It's a project of engineering and integration in inertial confinement. She explained why NIF cannot be escalated somehow to a commercial plant. The way to escalate that is through that project. NIF is an old machine, has limitations, and she reminded us that in April this year, NIF achieved a Q, scientific Q higher than 4. So they are optimizing the results, they are optimizing the performance of the machine, but has certain limitations. Which are the technology needed for commercialization? What needs to be improved? Which is the way to move to commercialization to inertial fusion is gas lasers. We have seen that this represents a revolution. Let's say it's the equivalent to the high temperature superconducting magnetic fields in magnetic. For inertial, these are these new lasers, more compact, more powerful. We need to be able to mass manufacture targets, and they are working with General Atomic on that, and the chamber, the new design of the chamber is much more optimized. It's liquid walls, where you need 2 beam ports instead of 192. Bottlenecks, target fabrication at scale to scale up to cheaper price. Right now, they are very, very expensive. Gas lasers open the door to optimization, and breathing blanket tritium. I would like to highlight that point because maybe yesterday we didn't put not enough attention. It was later on discussed, but finding this transversal topic where private-public partnership can be really useful, and even a cooperation between the private sector together with the public sector is needed because are transversal topics that are affecting to everyone. And she's highlighted this breathing blanket and tritium production where you have many gaps, technological gaps that basically affect to 90%, 95% of all the fusion companies. And to be able to answer that, you need huge investments in terms of testing capabilities and knowledge. It's something that the private sector probably cannot do alone, and the help and the cooperation with the public sector will be essential to push fusion forward. I think this is a really strong idea. Then we have a few remarks by Carlos Hidalgo, really clever and going to the point, that we need integration with ambition and credibility. He proposed this model of integration in a multidimensional space, physics and technology. All the two elements has to work together and be integrated together if we want the machine to work properly. And he also indicated this setup and integrated validation strategy, this modular validation going module by module, which I think is something very valid. So then we go to the materials hardware. We narrow down the topics. We all, by that time, understood that materials play a key role, that the breathing blanket, that the Bertol, auxiliary system, diagnostic, everything has materials. All of them, they are going to be in a hostile environment, depending on the position on the machine, more or less hostile, but we understand that all these materials and the fuel cycle needs to be studied because we have gaps. We have a presentation from, if I remember, Angel and Richard Pearson, they can correct me, where they were mentioning that the feasibility of fusion as energy source is controlled by 3+1 key parameters, tritium, and they mentioned self-sufficient, and later on it was added by Richard, if I remember correctly. This, in addition to the self-sufficiency, the supply, the use, and the management of tritium represent challenge. Previous facilities provide some information about how to do that thing, but not all the information. We have challenge in the tritium fuel cycles, the technical challenge, the operational and safety, and the strategic and commercial. So tritium is a big topic to study, and number of gaps are there, and I need to be fast, otherwise I will need much more time. So one of the key parameters for the reactor is the tritium self-sufficiency and the tritium handling, I would say in general, the availability, the efficiency, and the safety and the environmental plant. And we need to remember, and then Klaus Hersch passed me his slides, or his notes, the three major functions of the tritium breathing blanket is generate tritium, harvest the energy produced by the fusion reaction, and shielding in magnetic fusion. And talking to people, they were not having this idea very clear. Why a blanket is so important? It's because it's sort of the core of the fusion. You have to produce the tritium that your machine needs. You need to extract the power that you produce, and this is why you have the machine, and you have to protect the rest of the installation. And the conclusion was clear that we need to test materials and the proper environment, and machines like if-MIF donors types are needed. And a very important comment that came into the discussion is we need more than one if-MIF donors. If we want to be able to address and to provide enough data to the community, to the companies, we need more than one machine to be able to generate that data. In spillovers technologies, we have this good example of renaissance fusions. We have what we can do with liquid metal loops and enriched lithium. We were talking also about magnets and how many companies are producing, or a number of companies are producing high temperature superconducting coils and how this can be used out of fusion. It was highlighted that this magnet has the risk of not being okay for fusion due to, among other things, because the lack of supply chain of those in Europe. So it's something that we need to push and to start to create this supply chain to be as independent as possible, knowing that we live in a global world with being completely independent is really difficult. It was highlighted that cryogenic is a mature market, but high voltage development producing fusion can have another market. So there are a number of aspects of the technology that can be easily exported to other markets and have a source of revenue. We have, in the second part of the day, a block on investment. We went to public-private collaboration and then to purely the investment. I will go fast here. From the private-public collaboration, I would like to highlight these warnings of when you define how you should define a private-public partnership to avoid problems. It should be a clear goal. It should be a clear program. everything has to be very well understood by the two parties, the private and the public organization, and the interest of both organizations has to be aligned. If you are not able to have this clear, your private partnership agreement will not work. So keep an eye, it's not a general agreement, it's something very specific to do something very concrete, and these two things needs to be understood. Goals, interests, and how this research or this project is going to be aligned with your interests. And if it's not, then you should not do it. Finally, in the investment part, and I think this is probably the most important part for the startups that we have here, which is important for the investor. Peer review publication counts. That gives you credibility, and it makes you to be scientifically sound. So it's better to share your information to get that credibility, to show that what you are doing has some basis, it's true, it's real. You have to be able to make a project investable, and because of that, you need to put your project in a country that you have regulatory certainties. It's very difficult to sell a project that you say that you are going to build a tokamak, an accelerator, an inertial fusion device, if in the country where you are going to establish that doesn't have certainties in terms of regulation. And this is something that countries that want to be fusion countries need to push on that. We have been talking about the need of having a fusion-specific regulatory framework also, so I'm not going to repeat it. And then to commercial fusion, we have this step from the lab to Q higher than 1 to produce net electricity, related to the question this morning, and to be commercial competitive. It's coming back to the key, to one of the elements that Carlos mentioned in the keynote. So in all this way, we go from the research to the private-public partnership, where they are providing the help and the support from jumping from this Q higher than 1 until you can be competitive, and then you can get directly private funds. Very two important notes. To get investment, we need to understand the VC times. This is not 30 or 40 years. This is times of between 3 and 10 years maximum. And they want, at the end of the investment, cash or share in a public company as a return. They don't want to keep remaining the private ownership of the company. And in sometimes these times can be a little bit low, extended up to 18 years, if I remember, and Phil can correct me. In your case, it's something around 20-something years, so, but not beyond. So the project that you present to one of these VCs should be consistent what they are expecting. And that's all. Thank you very much.
Thank you. Thank you.